Hi, hello everybody. Welcome back to another session of Surface Chemistry presented by Anand Academy. So today's topic of interest is BET absorption isotherm. BET, where B, E, and T stands for certain names. Okay, so that is actually Bronner, Emmett, and Teller. So it is Bronner, Emmett, and Teller adsorption isotherm. Okay, so we already know that there are certain limitations of Langmuir adsorption isotherm. That is, they do not take into account the multi-layer formation. So here they do take into account the multi-layer formation of adsorbate on the adsorbent. Okay, multi-layer formation is considered. That is a major advantage. So for that, they have taken into account certain assumptions. Now, what are the assumptions? Let's note them down one by one. Okay, so please note the assumptions or the postulates, you can say. So the first postulate is the gas molecules, that is the adsorbate. Please note it down along. Gas molecules behave ideally. So it is said that before the interaction of the gas, I hope by gas you understand that this is the adsorbate. So these adsorbate molecules, before the interaction with the adsorbent surface, within themselves, there are no interactions. Okay, they behave ideally, meaning no forces of attraction or repulsion between these gaseous molecules. Okay, between the gas molecules. So they do not interact with each other even before the adsorption. That is one postulate. And there is another postulate which says that the adsorbed moieties, the adsorbed molecules, they also do not react with each other. Do not react with each other. Okay, I hope you understand the meaning. Let's say that you have a surface and you have the adsorbate molecules attached, adsorbed. So once they are adsorbed, they do not interact with each other. And even before the adsorption, also they do not interact with each other. They behave ideally is what is postulated. Okay. Next postulate. Each adsorbed moiety, each adsorbed molecule provides a new site. Provides a new site for adsorption, and this is the highlight of BET adsorption isotherm. So earlier and all, the assumption was if you had a particular layer, let me erase this. If you had a particular layer of adsorbent surface, it was capable of forming a monolayer only. Correct? So this was the earlier case, but now what they're saying is, if you have a surface, the surface will have, let's say, 1, 2, 3 active sites. And upon these active sites, the adsorbate molecules can come. Apart from that, on the top of this gaseous molecule itself, another gaseous molecule can come and attach. Okay, that means each gaseous molecule which comes and adheres to the surface acts as the next active site. So since the gaseous molecules itself act as an active site, which means the active sites are capable of absorbing next set of gaseous molecules. So that leads to multi-layer formation. That's it. So you write that down. That is multiple multiple adsorbate gas molecules can attach at each site until liquefaction happens. Liquefaction means that is a saturation. Liquefaction of gas. So if you can see, this is the active site. You can see this is one, this is second, even a third moiety can come and sit over here, no problem. So multiple gaseous molecules can come and adhere to one single site because this gaseous molecule itself can serve as another site. That's fine. And hence multilayer formation is possible. Now, even though let's say here you have A, B, C, three sites on the adsorbent surface, all those sites are equivalent. Okay? All the surface sites are equivalent. And last, what they say is the adsorbed molecules are immobile. They cannot move once they are adsorbed. Adsorbed molecules are immobile. That's it. Okay. Now we need to learn the BET equation. No way out, you have to learn it. Okay? You have to learn it. And the equation is, see, I'll compare it with Langmuir so that you can understand. For Langmuir adsorption isotherm, the equation is theta is equal to Kp by 1 plus Kp. Okay. Where theta is the surface coverage, extent of surface coverage, P is the pressure of the gas, and K is the Langmuir's constant. Correct. Now, if we have to write the BET equation, okay, here what we have is, according to the BET equation, please observe, so theta, that is equal to K1P. I'll explain what K1 is. K1P divided by, here it is 1 plus Kp, right? Instead, what are we going to do is, you will write this K1P as it is. Instead of 1, what you have is 1 minus P by P naught plus into 1 minus P by P naught. This is how that equation is written, where P is the pressure of the gas, P naught is something new, correct? P naught is the saturation pressure, that is the maximum extent to which the gas can absorb onto the surface. That's all. Saturation pressure. After this pressure, the gas will liquefy. Okay? And K1 is the first equilibrium constant. First equilibrium constant. Meaning, if you have a gas plus substrate initially, it forms GS, which is in equilibrium, of course, and the equilibrium constant is K1. This is the first step. In the next step, this GS reacts with another gaseous molecule, which is again in equilibrium and forms G2S. This is the second step, and the equilibrium constant is K2. So in BET, what you have is the equilibrium constant for the first step into the pressure of the gas divided by 1 minus P by P naught into 1 minus P by P naught plus Q1P. This is the BET equation. All right. So what are the conditions under where the BET equations transform into Langmuir? You can get a question. So let's repeat the equation. We know the BET equation is K1P divided by K1P. And then you have to add a new term, which is 1 minus P by P naught. Here also you multiply it. 1 minus P by P naught. Okay. This is the BET equation and this is equal to theta. The moment P by P naught becomes 0, if P by P naught becomes equal to 0, see what happens? It becomes K1P divided by 1 minus 0 is 1 and 1 plus K1P. That is equal to theta. So this has now transformed to Langmuir equation. So when did it transform? When the value of P by P naught is equal to 0. When will P by P naught be equal to 0? P is the pressure of the gas and P naught is the saturated pressure. Correct? Saturation. Saturation pressure, that is the pressure at which the gas cannot exist as gas anymore. It converts to liquid. Saturation pressure. So if this P by P naught has to be 0, then P naught has to be infinity. P naught has to be infinity. That is the moment where this, so certain people write P naught down, certain people write P naught at the top. You can use whatever notation. Okay, so P naught when is infinity, then your BET isotherm turns out to be a Langmuir equation. Okay. All right. Now, so nowadays there is another modified version of modified version of BET equation as well. Let's learn that. So by now we know that BET equation. I'm writing it again and again so that you can repeat it in your notebook, which will help you learn. So this is the BET equation that we have learned. Now there is a modified version of this. Okay, there is a modified version of this. For this, you have to understand certain things. We already said that if we have a gas in combination with a substrate moiety, it becomes GS with a equilibrium constant of K1, right? And K1 over here is GS concentration divided by concentration of G into concentration of S. We know that. Now for the second step, this GS combines with another G and forms G2S, and this is equilibrium constant K2, where this is equal to G2S divided by concentration of GS into concentration of S. Next step, let's write one more step. G2S can combine with another gaseous moiety with a third equilibrium step forming G3S. And the equilibrium constant over here is equal to G3S divided by G2S into G. Okay, I wrote S over here. It is actually G. Okay, sorry, please make the correction. Please make the correction over here. It is G. Okay. Now, until how long will this gaseous molecule come and absorb? There will be a particular point where this goes on. And that point is when the gaseous molecules, what you have taken, becomes liquid. Okay. And that equilibrium process where the whole gaseous molecules that you have absorbed onto the surface becomes liquid, that pressure is known as the saturation pressure. And correspondingly, that equilibrium constant is KL, and KL is equal to concentration of the liquid divided by concentration of the gas. Now, from basics of equilibrium, always the concentration of liquid is taken as unity. So KL is equal to unity 1 by the pressure of the gas when it turns into a liquid is saturation pressure. So KL is equal to inverse of saturation pressure. KL is the inversion of saturation pressure. Now, what is the order of these equilibrium steps? Which one would be the fastest? Of course, the first. That is the fastest, followed by K2 and then K3. And then approximately whatever equilibrium steps that you have will be nearly the same. K4, K5, everything will be the same until liquefaction. Okay, so this is the order of equilibrium. Okay, now on the basis of K, L, P naught, etc. Again, there is a modified version of BET equation. Let's write it down. So modified BET. You get graphical questions from here, so important. Modified BET equation is P by V absorbed P naught minus P is equal to 1 by VMC plus C minus 1P divided by VMC P naught. In earlier days, if you do not learn this equation, it was fine. But nowadays, you get a lot of questions from here, so you cannot skip this. You cannot skip this. Okay, so this is the saturation pressure, P is the pressure of the gas. V absorbed is the volume of gas absorbed, and Vm is the volume of gas required for monolayer formation. Right. Required for monolayer formation. And you have a constant C over here. The constant C is the ratio between the equilibrium constants, which is K1 by KL. K1 is the equilibrium constant of the first step and KL is the equilibrium constant of the last step until the gas is liquefied. Okay. So this equation is important. Why? Because you get graphical questions from here as well as conceptual questions. So if we have to plot a graph, if you plot a graph between P by V absorbed P minus P naught versus P by P naught, you can see that this is along X, this is along Y. So this is of the form Y is equal to mx plus c, where it is a straight line whose slope is c minus 1 by c into Vm and whose intercept is 1 by cVm. You will have to learn it. There is no equation out. There is no way out. So you have to learn this. P by V absorbed divided by P naught minus P is equal to 1 by VMC plus C minus 1 P by VMC P naught is the BET equation. Very, very, very important. Okay. Now, this is very similar to that of the Langmuir equation. I'll explain how. Please write down the equation once again so you learn it. P by V absorbed into P naught minus P is equal to 1 by VMC plus plus C minus 1 divided by VMC P by P naught, right? I hope I have written C minus 1. Okay, yes. Okay, now imagine that the saturation pressure is very high. If the saturation pressure is very high, P naught will be very much higher than that of P, correct? Then P naught minus P will approximately be as P naught itself, because now the value is so high that this P can be neglected. So if that is applied over here, the modified BET equation becomes P by VAD P naught is equal to 1 by VMC plus C minus 1P by VMC P naught. Now multiply the whole equation with P naught. Multiply the whole equation with P naught. So you multiply it with P naught here, you multiply it with P naught here, and you multiply it with P naught over here. What do we get? P by VAD is equal to P naught by VMC plus P naught gets cancelled. C minus 1P by VMC. Okay. Now, we know that C is equal to K1 by KL and KL is equal to 1 by P naught. You know this. We have explained this. So if I put this value of KL over here, C becomes K1P. K1P naught. Correct? It becomes K1P naught. So C is equal to K1P naught. So we have something called C minus 1 over here. So C minus 1 means K1 P naught minus 1. We already told that P naught is very high. We already told that P naught is very high. So K1 P naught minus 1 can be approximated as K1 P naught. So C minus 1 can be written as just C. And C is K1P naught. So let's put in the values again. So this becomes P by VAD is equal to P naught by VM K1P naught plus again C minus 1 is approximated at C, which is K1P naught P VM K1P naught. K1 P naught, K1 P naught gets cancelled, P naught gets cancelled. So see what you have. P by VAD is equal to P by K1 VM plus P by VM. So do you remember this equation? This is again a Langmuir equation whose graph we have already learned that if you plot a graph between P by VAD versus P, P by VAD versus P, you get a straight line whose slope is 1 by Vm and whose intercept is 1 by KVm. So you can see that at very high saturation pressures, the modified Bett equation becomes same as the Langmuir equation. I know this might be a bit tough or lengthy for you, but then you just pause the video, rewind it, watch it again, write 2 to 3 times. It's going to be okay. Okay. Once you learn the derivation like a story, it is going to be okay. So don't stop this just because you feel it is difficult. Questions. Okay. So what have we discussed? I'm just summarizing whatever we have learned. So that equation, there are two forms. One is K1P divided by 1 minus P by P naught into 1 minus P by P naught plus K1P. This is the first thing that we learn. Right. Now, the next thing that learned is the modified Bett in terms of P, V, D, P naught, etc. So, according to that, P by VAD P minus P naught, that is equal to 1 by VMC plus C minus 1 VMC P by P naught. Correct? Whatever the formula is, at higher saturation pressures, the Bett equation transforms into Langmuir equation, becomes Langmuir equation. Right? So you have to learn this here when you plot a graph between P by VAD, P minus P naught versus P by P naught. This is going to be your slope. which is C minus 1 by DMC, and this is going to be your intercept. Okay. There is a bit more from Beck's theory. I'll be explaining that in the next video. That's all. Thank you.